Alright, so we're given a number, and we're supposed to return the square root of it, of that number x, without using any built-in square root or exponential functions. So the way I did this was, I realized that given a number, let's just pick a perfect square like 16. You look at all their factors, it's the factors of a perfect square, right? 1, 2, 4, 8, 16. And almost all of them will have a matching factor, right? 1 times 16 equals 16. 2 times 8 equals 16. 4, though, doesn't have another number that matches it. It's just 4, right? 4 times 4 equals 16. That's kind of the idea of a square, of a perfect square, right? It's a number times itself equals, the square. So the idea is to take the number, let's say x, right? X equals 16 in this case, to go through all the factors, and pretty much if the factor, if x divided by that factor equals the factor, right? This is the same number, then we found the perfect square. So that's part of the problem, right? Part of the problem solved. When it's a perfect square, that's all you need to do. When it's not a perfect square, you need to do a little bit more. Like if you have a number like 8, it's not a perfect square. No, you can't find a single number that multiplied by itself equals 8, right? It's like they say, the answer is 2.82842, blah, 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 which would be truncated to 2. So that's another little problem to solve, but it's doable. But let's just take the simple example of the perfect square first, because it's an easier problem to solve. So one thing to realize is you can actually make the code run a little bit faster by realizing that when you're doing this, right, like I said with 16, 1, 2, 4, 8, 16 other factors, you don't actually need to go all the way up. You don't need to go from, like, say 1 all the way to 16. You don't need to go from 1 to x, right, in a for loop, for example. You can just go up to the square root of 16, which might sound a little silly considering we're making a function and we're supposed to find the square root. So the idea is we probably don't know the square root, but what you can do for your for loop, you can actually have it go, starting at 1. What you can do, instead of saying, normally if it was a different type of problem, you'd want to say as long as I is less than or equal to the square root of x, right? But we can't do that in this case. So what we do instead is, you could see it like this, right? If we did like I just wrote it, as long as I is less than or equal to square root of x, you just do a little bit of algebra, right? You square this, and you square both sides, right? Which would become I squared less than or equal to x, right? So that's what you do in your for loop. You say as long as I times I is less than or equal to x, and then you increment I each time, right? So that saves us a little bit of time, and that makes the loop O of a big O of square root of n instead of big O of n. So anyways, but what do you actually do in the loop, right? Well, all you do, first you check is the current value I, the current potential factor, is it an actual factor? So you do that by checking, if, let's call this x, if x divided by I equals 0, if it's a factor, right? And why don't I actually just write this in the editor? So the idea is, so starting at 1, because we don't need to check 0, because 0 is not a factor of any number other than 0, I guess. So we'll do that I times I is less than or equal to x, pretty much saying go do all the numbers from 1 up to and including the square root of x. Right, and of course in a perfect square, when we get to this point where I times I equals x, that's our square root that we can then return. But so, like I said, if x mod I equals 0, right, then we'll call this the other number, other factor. Other factor meaning, say we're on 2 here. The other factor would be 8, because 16 divided by 2 equals 8, right? So what we're doing is saying other factor is that other number. To get that, you do x divided by divided by I. And if other factor equals I, if it's the same number, right? If instead of it being, say, 2 and 8, it would just be 4 and 4, because of course 16 divided by 4 equals 4. So this would be I, this would be other factor, they're equal. Therefore, we know we found the perfect square, so we'll just return that number, right? Just return I. Now that's great, and that solves a problem for perfect squares, right? There's two more problems we need to worry about, and one is I've briefly mentioned, which was when you don't have a perfect square, right? When you say you're doing this process for, say, 8 or 10 or whatever, right? Another problem is integer overflow. So let's do the non-perfect square first. So the idea, because we'll never actually get to a point where this is true, this line right here, this will never be true. What we need to do is kind of keep track of our best options, right? So let's do 8. Let's take 8 as an example. The factors of 8 is 1, 2, 4, 8, right? 1 times 8 equals 8, 2 times 4 equals 4, right? So the square is somewhere in here, right? The square is 2.3 or whatever, which means our best answer that we can give here is 2, because just the nature of the problem, we're returning an integer. It's pretty much the square root truncated, right? You wouldn't want to return 4. That number's too big. So the idea is you want to keep track of each best factor for each iteration. So we'll create a variable called best factor. We'll set it to 0, which will work in the case where we get 0 as x. It'll just return 0, blah, blah, blah. Doesn't matter. Just set it to a value. And what we'll do is each iteration, we'll just set best factor to I. Right? So each time you go through, you say, okay, best factor, let's just call it BF. And let's just say we're working through this. Right, so we're at 1, okay, BF is 1. We go 2, okay, BF is 2. And now, because of this little loop right here, this I times I less than or equal to x, we're not going to get to this 4. We're not going to get to 3 or 4, because as soon as we get to I equals 3, that would make I times I equals 9, which is not less than or equal to 8, right? So we'd only get up to 1 to 2. We'd do 1 and then 2 in this case. 2 would be our best factor, so by the time this loop breaks, because this condition is no longer true, we'll have the best factor, right? And we'll just return that. So we solved the problems of the perfect square, the non-perfect square. Now one more problem is integer division, and I can show that by trying to submit this. We should get a failed test on the about 2,147,000 or whatever it is. Right. See, this is failed input, because here's why. So we pretty much are working up our way, right? Just like the for loop does. When the x is this number, which is the integer max, right? When it's this number, 147,483,647. The square root of this, let's just call it x, equals, let me just calculate real quick. Does this thing even have square root? So 2147483. It's around 46,000 square root. Right. So it's 46,340.95. So when we're running through our loop here, right, we'll get up to the point where I equals this number with minus the decimal, right? And that's all fine and dandy, and that works, right? I times I just becomes integer max, which is a valid integer. It's not going to overflow. The problem is, because of this 0.95, this number is not the square root of this. So we're going to do another iteration of the loop, right? So then we're going to do I equals 46,341. And when we try to do this little bit up here, this little second part of the for loop, when we try to do I times I, this will do 46,341 times 46,341. And because we know that this is the square root of integer max, we know that this number times itself is greater than this, which means it's going to overflow. So to avoid this, we need to treat I as a long. Now instead of changing this to a long, because we need to deal with turning it back into an int later because we're returning an int and blah, 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 just cast this little bit as a long, right? And that'll deal with it. So now I is still an integer. It's completely normal and fine. But when you're doing this little check here, it treats this as a long, which means it won't overflow, which means we'll be able to validly compare it to x, right? So that should solve the problem of the integer overflow. So now this should pass. Yeah, there you go. Now, I believe the time complexity of this is O square root of n. Oh, I can't delete this. Come on. Right? Time big O, the square root of n, because we're going from 1. Worst case scenario, which would be I guess anything. A perfect square would go up this high. Anything would go this high, but we go from 1 to, as long as I times I is x, which is the same. Remember, I times I less than or equal to x is the same as, we can just square root this is the same as I square root, or I is less than or equal to the square. Wait, what am I saying? No, it's this. I'm brain dead. Which is saying this is just square root of n iterations. So the time complexity, because everything else is constant, is O of n space is constant O of 1.